Hi everyone, welcome back to another AP Calculus video. Today we're going to dive a little bit deeper into vectors and how we can do some calculus with vectors to find displacement, to find the distance that a particle has traveled along its pathway. And remember that a vector is simply here for our purposes just an extension of parametric equations. It's an ordered pair of equations that tell us what's happening specifically with the left-right motion, that would be the x-coordinate, and the up-down motion, that would be the y-coordinate. So let's recall just a few basic calculus items here. Remember that displacement of an object is simply the integral of our velocity function. So if we know about the velocity, it all starts with velocity. If we integrate a rate, we get the amount of change. So if our rate is velocity, we get the displacement when we do our integral. So how much has the particle moved from time A to time B? And remember, if we have an initial position, we need to take that displacement and add that on to find our final position. One of the ways that we've been expressing this in class is simply this. If you have some sort of integral where you're given a position at time A, you're going to add to it the integral from A to B of our velocity function with respect to t. So in general, any function this works for would be this. You'd have f of b equals f of a, the initial condition. A is always our start, so what we're starting with, plus the integral from a to b of f prime, so the derivative from a to b. So this is our generalized form for finding the amount of change. So when we have these problems, when we're dealing with this, this applies directly to vectors and how we treat vectors and how vectors behave. So when we're dealing with our vectors, what we want to understand is, hey, we're going to follow the same calculus rules, but this time we're going to have some sort of vector valued function. So it's going to look like this: v of x, comma, v of y. And our parameter is going to be t, for time, usually is how it works here. And so if we want to find our displacement, the displacement will simply be an ordered pair of integrals from time a to b. So we'll integrate the x equation with respect to t, and then we'll integrate the y equation with respect to t. So it's like we have double the equations. And that's how we're going to evaluate, that's how we're going to find the displacement when we have vector valued functions. So it's an ordered pair of integrals, much the same way that displacement with just a function, if we just have a function with respect to time, our displacement would just be the integral. Well, here the displacement would be an ordered pair of integrals. Now, if I wanted to find the final position, I would take this integral and I would add it to my initial position. So this particular rule still applies. This is just how far my particle has moved. This tells me how far my object moved. So you have to have a starting position, so it tells you the amount of change. So the x-coordinate is how much did the x-coordinate change. The y-coordinate, the y of the displacement tells you how much the y value changed. So this is how we find displacement. Now, there's more that we can do here. We can also talk about total distance. Now, the total distance that an object traveled would be like if I have an object that's moving in space, and I know it's following some parametric equations, and here this is point A, and this is point B. And it's traveling, and maybe it loops around, and it ends at point B. If I want to know the total distance it traveled, that's different from the displacement. To find the displacement, remember that the displacement, this would be the integral from a to b of v of x of t dt. So it's telling you how far to the left did you move from point A to your final point B. And then this is your integral from a to b of your y vector. Now the total distance you travel is the blue path along the curve. So if you want to know the total distance, like how many steps did your particle take as it looped around and did all the crazy stuff, Remember, we talk about displacement as being, at the end of the day, your displacement is usually 0 because you start the day getting out of your bed and you end it getting back into your bed. But the total distance is the absolute value, so it doesn't account for direction and canceling out distances. It just says, what is your total step count at the end of the day? Well, the total step count is the length of this little blue curly segment. And the way that we find that is we find the absolute value. We find the integral of the speed vector is really what it is. And so if we integrate our speed, that's what we found yesterday. So remember, this right here is speed. If we integrate our speed, that tells us our total distance. So remember, the speed is the absolute value. It's always a positive scalar. And when we integrate a rate, it tells us the amount of change. Well, if we integrate just velocity, we get the amount of change in x and y. When we integrate speed, we get the total number of steps we've taken. So this formula right here is really critical in finding the total distance that we traveled. And this is a really common question to pop up on the AP exam in terms of what you're asked to do with vectors. So once we have this equation down, and you can pause the video and copy it if you need to, let's try an example. So here I've got a particle moving in a plane with a velocity vector given here. At t equals 0, the particle is at the point 1, 5. This is my initial condition, position. I want to find the position of the particle at t equals 4. So what I'm going to do is I'm going to find my vector. Here's my vector equations, right? So I'm going to find my position, my amount of change, my displacement. The displacement, and when I show my work, I kind of want to show it as the two integrals. So the displacement from the starting time, t equals 0, to the time I want to know about is this, 0 to 4, and I'm simply going to integrate the x coordinate function. There's a lot of stuff going on in there. Close that, dt. And then I'm going to integrate separately, same limits, different function, 2t minus pi times the sine of pi t. Now there's a lot going on in here, so I'm going to be super duper careful. And on your AP exam, you are always invited to kind of use the shorthand. We commonly call this v of x and v of y. So you can use those substitutions if you're doing a setup that's a calculator active question. Now this one I would kind of consider to be a calculator active question. So in this case I would probably go to my calculator and I would type some things in and I would get my values, and using my calculator, using Math 9, evaluating these, use the letter x, you're going to find that this particular integral works out to be 8. And the y integral works out to be 16. Now this is just the amount that we've shifted. So wherever we started from, we moved 8 to the right and 16 up. That's the amount of change. Now to find where we landed, we have to take our initial position. So our final position is simply 1, 5 plus that shift of 8, 16. So my final position, and again, rounded brackets, squared. When you're talking about position, usually we'll switch to rounded brackets. It's semantics. But we basically, this is where we land. And that's my final position, okay? So the displacement is the 8, 16. I moved over 8, up 16. This would be my final position, rounded brackets, squared off, whatever brackets. But this is where we land. Now, part B says, what is the total distance traveled? Well, to find the total distance, that's where I'm going to integrate my speed from 0 to 4. So let's go ahead and set that up. To integrate the speed, I'm literally going to take the equations and plug them in. And again, let's not write, this is a calculator type question. So I'm just going to say v of x squared plus v of y squared dt. And this is another case where I would plug it into my calculator. I'd actually put the v of x into y1, I'd put the v of y into y2, and I'd use that feature on my calculator to save myself some time. Now I'm not going to do that here because the assumption is if you've gotten this far into calculus, you should know how to do that, and you should know what I'm talking about. But again, this is v of x, this is v of y. Put it into y1 and y2. It'll save you from typing it in over and over again and making a mistake. So ultimately, when I do this integral, when I use Math 9 in my calculator, I'm going to end up with this. And this would be the integral that I'd want to show on my paper on a free response portion of the exam. 33.533 is my rounded answer. So that is my total distance. That's how many steps we took at the end of the day. That's what I'm looking for. And this is the work that my AP reader would be looking for on a free response question. Now, part C says this. Find the vector that represents the path of the particle from 1,5 to 921. Then graph it in your calculator. Okay, so this one is asking me to basically take the equation and we want to be able to find the path. We want to trace the path. So we're given velocity. We want to find position. So let's recall that if the derivative of position is velocity, then when I integrate velocity, I get position. I get the change in position. So essentially, I'm looking for a function that will give me, I'm looking for the antiderivative. So I'm going to take that equation and I'm going to find the antiderivative. So recall, this is what we started with. We have t minus 3 pi, so much going on, and then 2t minus pi sine of pi t. All right, so there we go. So my position would simply be the antiderivative. So kind of the work that I'd show is this. I'd say, well, it's the indefinite integral of this. So here's my formal comma 2t minus pi times the sine of pi t. So much going on. All right, so let's go ahead and anti-differentiate. And remember, we're going to have a constant of integration here. So here we go. This will be t squared over 2. Oh, and then this 3 pi, that's just a constant. It's a number in the front. So I'm going to have minus the antiderivative of negative cosine. Remember our wheel of sines here. We've got sine, cosine, negative cosine. So the antiderivative of negative cosine is sine. So this would be minus 3 pi sine of pi over t divided by pi. That would be the u sub that I'm kind of skipping, plus c, comma, and then we would have t squared, or 2t squared over 2, it would be just 2t squared, minus the antiderivative of sine is negative cosine, so this would turn into a plus pi times the cosine of pi t divided by pi, plus c. Oof. Now I need to solve for those constants of integration. Well, I know that my initial position was 1,5 when t was 0. Okay, so I'm going to use that. I'm going to set the x coordinate equal to 1 and the y coordinate equal to 5. So here we go. T squared over 2, and I'm going to cancel this pi. So when t is 0, so that's going to be 0 minus 3 times the sine of 0 plus c equals 1. So sine of 0 is 0, so c equals 1 here. Over here, let's see, we're going to have to plug in 0 again. So we have 0 plus pi times, oh, that pi cancels, plus the cosine of 0 plus c equals 5. Well, the cosine of 0 is 1, so that means c here would be 4. So these are different constants. You can call them constant 1, constant 2, it doesn't matter. But essentially, here is my position vector. That was a lot of work for this. T squared over 2 minus 3 sine pi t plus 1, comma, t squared plus cosine of pi t plus 4. So there's my position vector. Now let's look and see what we needed here. Did we answer the question? Find the vector that represents the path of the particle. Done. Then graph it in our calculator. So let's recall how to graph some parametric equations. This would be a good little practice problem to make sure we know what we're doing here. So let's get out our graphing calculator. Now when we're graphing parametric equations, we want to make sure we're in the proper mode. So I'm going to go down to the function mode here. I hit my mode button, which is right next to that blue second key. I'm going to go over to parametric. Make sure I'm in parametric mode. I'm going to go to y equals. I'm going to clear anything out that's already hanging out in there. And I'm going to just enter them in. And so we've got x squared. So t squared over 2 minus 3 times the sine of pi t plus 1. So there's my x1. And my y1 would be t squared plus cosine pi t plus 4. Now, when I do my window, remember we're dealing with, we want the path from 0 to 4. So I think that's what we had been talking about initially. So from t equals 0 to t equals 4. So I'm going to go to my window, and I'm going to make sure that my t max and my t min are just from those time periods. I'm also going to make sure that my t step is sufficiently small. Usually it's 0.13. That's the default. Sometimes we need to change it if our curve doesn't look smooth and curvy. We may have to reduce that even smaller. But once we have our window set, and I'm actually going to change the window. I happen to know what's going to happen. And I'm going to change my window to -5 and 15 for the x. Now, you would find this out simply by hitting the graph button and seeing that it doesn't contain the entire graph. So you'd have to play around. And I just happen to know that these particular windows will work. And so I'm going to hit the graph button. And this is the path of the function. It's a little curly Q. How cool is that? So the distance traveled is, if that was a string and we stretched it out, that's how long the string would be. That's our total distance. It's the length of the parametrically defined curve. That's interesting. Another way to think of it. It's the length of the curve, right? So in the application of velocity, position, and acceleration, when we're dealing with that type of application, the length of curve formula that we learned with parametric equations is simply the total distance traveled by a particle in motion. So they're all related, and it's just a matter of how are we going to apply it. So this is how we do some calculus with these types of problems. This is how we find our total distance. This is how we work with our vectors. So everything we know so far about objects in motion, it works the same in vectors, and the main difference being now we have an x and a y equation, and we treat it the same, and essentially our calculus knowledge gets applied here to 2 equations instead of 1. You're going to get better at this the more you practice. You're going to see lots of these vectors show up all over the AP exam, asking you to find total distance, asking you to identify velocity and acceleration vectors, and also asking you to solve for a position vector using integration. So all those techniques that we're familiar with from functions apply right here to vector valued functions and vector equations. So keep practicing, keep at it. You can do this. You've got this.